go over an example on how to build a confidence interval because I feel like that's an important topic that can sometimes be confusing. And so here's our question. We have the standard deviation of weights of newborn elephant calves is known to be approximately 15 pounds. Okay, we wish to construct a 95% confidence interval for the mean weight of newborn elephant calves by weighing 50 elephant calves, resulting in a sample mean of 244 pounds. So in other words, we're trying to use our sample mean here of 244 pounds to make a judgment on what the true population mean is. Okay, now what I think is helpful is to draw a picture to try to get an idea of what we're saying here. Okay, so here's a normal curve. We know from the central limit theorem that is, if we keep taking samples, that the averages of those samples will form a normal curve. We're going to use our sample that we came up with to estimate the true mean, so 244 pounds. That's our sample mean. Alright, now what we want is we want a 95% confidence interval, which means that we want to find two numbers right here and right here, such that when I mark out those two numbers, I have now carved out 95% in the middle here in area, okay? And so that means that we would have a 95% chance of saying that the true mean is between these two numbers. Now, how do we calculate those two numbers? We need to find something that we call our error bound, an error bound of the mean. And we'll calculate that error bound in each direction. And so once I figure out those numbers, I'll have x bar plus my EBM, and I'll have my x bar minus my EBM. And those will be the two numbers that we sought. Okay, now how do we calculate error bound? Well, the error bound is going to be the number of standard deviations times my standard deviation. Now, with the central limit theorem, we know that this is going to be a normal curve. The means are going to follow a normal curve with an average of mu, and the standard deviation is going to be sigma over root n. So here, the standard deviation will be sigma over root n. How do I calculate standard deviation, or the number of standard deviations, is with a z-score, since I'm in a normal curve. And we call that z alpha over 2 times, again, my standard deviation is going to be sigma over root n. Okay, now what's alpha over 2? My confidence level is what this 95% is. Alpha is the opposite of that. It's called my significance level, and the significance level shows up in my tails. So the alpha over 2 is referring to the area of that little tail right there, which will also be the area of that tail there. Okay, now since we're dealing with a normal curve, we're going to have to use a table to calculate that z-score. Alright, so let's get started. So I think there's an easy process to do this, a 5-step process. The first one is to identify what we need in terms of our numbers. So we need the mean, which is 244. They gave us a standard deviation of 15. We have n, the number of elephants that we test, are 50. Okay, we have a confidence level of 95%. And if they don't state a confidence level, we know that 95 will be the default. And so we have an alpha value of 0.05. So that kind of fills in these values on the graph that we highlighted. Okay, now, secondly, we need to find our z-score. We need to find our z alpha over 2. And that is always based on our confidence level. So to do this, we need to get a table of our normal curve, and I have one here. For my table, remember that we have here, we have 0.95 in all of this area here in the red. But actually my table will only give me from 0 up. So this blue region is actually half of 95, which is 0.475. Okay, so with that in mind, let's look at our table here. I'm looking for 0.475 in the table. And as you look, if you notice, for a value of 1.96, we have exactly 0.47500. So that tells me my z-score of 1.96 will guarantee that I have 95% in the middle. So let's use that as our z-score. And so we see that our z-score then is going to be the 1.96 from the table. Okay, now thirdly, once we have that, we need to go ahead and calculate our error bound. Again, this is that distance going from our mean up to these numbers in both directions. And we said the error bound was, again, the z alpha over 2 times sigma over root n. We have that information. We know that z alpha over 2 is the 1.96. We know that my sigma is 15, and we know that n is 50. So I have 15 divided by the square root of 50. And this is a total calculator move, so make sure that you get this right. You need to practice this in your calculator. You should get approximately 4.1578, and I like to round to 4 decimal places. I think that gives me a lot of safety. Alright, now part 4 then, I now have this value, this distance. The EBM is the distance away from the mean. So all I need to do now is to say sample mean minus EBM and sample mean plus EBM to get those two numbers that I was looking for. Okay, so remember my sample mean was a 244. So that's minus that 4.1578 and plus the 4.578. So I get 2.39.84. And I'll go just round it to 2 decimal places and 244.84. Now, how many decimal places do you need to round it to? It just kind of depends on the context, and you kind of just get that as you go. Here with pounds, I think 1/100 of a pound is pretty good. Alright, so lastly, we're not done until we communicate your result, and we communicate your result with this boring sentence. With 95% confidence, the true mean weight of newborn elephant calves is between 239.84 pounds and 244.16 pounds. What we're saying here is that we believe with our sample of 244 pounds that we have a 95% chance of saying that the true mean is going to be between the 239.84 and the 244.16 pounds. We only have a 5% chance of being wrong here, and we only tested 50 elephants. So that's pretty impressive. But this is the idea behind confidence intervals. Now, if you go through this 5-step process like we did, I think it clarifies this pretty easily. We can test for the mean like we did here. We can test for the mean with a small sample size, which all we'd have to change is using a t-score, or we could test proportion. And the only thing that changes there is our standard deviation has a different formula. Other than that, it's all the same. If you have any questions on this, I'd be glad to help, and thank you for watching.